Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the great stuff. This is the AAS Journal Author Series, and I am super happy to have Erin Boettcher with us today. Hey, Erin.
Hey, thanks for having me.
Well, thanks for agreeing to talk about your very lovely article, which we'll get to very shortly. Erin, where are you located at?
So I'm currently in Greenbelt, Maryland.
Okay, cool. Working for NASA?
I am. I'm a postdoc at University of Maryland in College Park, and also at Goddard as well.
Very cool. Very cool. Let's see. It is September 7th, so we're a little after Labor Day in the U.S. anyway, as we shoot this. And how is summer going on the East Coast?
It's going well. We've had some hot spells here in the DC area. Had our share of the humidity, but yeah, nice to have a sense of a little bit of fall in the air. So.
Ooh, okay.
Yeah.
I think the leaves are probably turning color a little bit, probably north of where you're at, yeah?
Yeah, probably just a bit.
Yeah. So let's see. I'm in Phoenix. We are still in full rolling summer. But I do hear up north around Flagstaff, whole observatory and whatnot, the trees are starting to do their thing, starting to turn because they're a little bit higher than we are at 6,000 feet or so. Very cool. Good. Erin, what do you like to do for research?
So I'm interested in galaxy evolution, primarily from the observational standpoint, and especially interested in the role of gas and gas physics in galaxy evolution. So studying how the stellar components of galaxies and the neutral gas reservoirs or multi-phase gas reservoirs of galaxies co-evolve to shape the star formation histories.
Cool.
And primarily low redshift.
Very cool. Very cool. And that is going to bring us to this very awesome. This is an APJ letter. It's open access, people. Open access era, so you can go get a copy for free. Go grab one. Discovery of a damped Lyman alpha absorber originating in a spectacular interacting dwarf galaxy pair at Z equals 0.026. And Erin, take us away.
Thank you. So as the title says, this is a case study. We're looking at this particularly interesting interacting dwarf galaxy pair at relatively low redshift, about 0.03. And this is a system that hosts a damped Lyman alpha absorber, so a neutral gas absorber. And I think what makes this a particularly exciting system is that we have quite a broad range of observational probes of this system, both for the stellar content and for the multi-phase gas content, both in and around these galaxies.
Cool.
And this lets us put together like a particularly detailed picture of the nature of these DLA host galaxies and let us sort of disentangle some of the physical mechanisms that give rise to the DLA, which is often quite challenging to do for DLA host galaxies.
Okay, cool.
So this comes from a collaboration between collaborations. So there's two teams that contributed to this work. One is the Cosmic Ultraviolet Baryon Survey, or CUBS. And this is a program that's led by Xiaowen Chen, Gwen Rudy, and Sean Johnson. And this program is using Hubble COS to look at the intermediate redshift circumgalactic medium redshifts 1 and below, using primarily absorption line spectroscopy as the tool, and pairing that with deep galaxy redshift survey information to be able to get at the coevolution of the CGM and their host galaxies.
Nice.
And the other collaboration that's involved in this work is the Meerkat Absorption Line Survey, or MALS. And this is being led out of IUCAA by Gupta and Shriyanan. So this is using the SK precursor facility of the Meerkat array to also to study the gas content, particularly the neutral gas content of the universe, redshifts below about 2, primarily using H1 and OH absorption as the tracer, as well as H1 21 centimeter emission in the local universe.
Nice.
So both of these programs are interested in this question of how do galaxies co-evolve with their gaseous reservoirs. So we have a great team here from both those collaborations all over the world, which has been great to be able to work with so many people. And this particular study came about because this particularly interesting system happened to be in the foreground of a quasar that's both UV bright and radio bright. So it was included in both the Cubs and the MALS samples.
Nice.
I'll talk a bit about the overall motivation. So in general, we're interested in better understanding how the neutral gas that ultimately fuels star formation cycles between galaxy disks and their surrounding environments, and how this shapes the star formation histories of galaxies. And a particularly useful probe of this neutral gas are the damped Lyman alpha absorbers. Yep. So these are neutral absorbers, column densities in H1 generally greater than about 20.3. And they're thought to trace a significant fraction of, dominant fraction of the neutral gas in the universe. So these are, we can detect these at high redshift from the ground in the optical, given the wavelength of Lyman alpha. So we have significant statistical samples at high redshift. So to detect them at low redshift, we need the unique capabilities of Hubble in the ultraviolet to detect them redshifts below about 1. So we have fewer statistics at lower redshift, but we're able to study the host galaxies of these absorbers in much more detail. So we're particularly interested in studying this galaxy gas coevolution to characterize this population of low redshift DLA host galaxies. And there's been quite extensive work on this in the literature that generally suggests that these host galaxies are quite diverse. They have a range of colors and luminosities. They seem to be found in both the fields and in the group environments. But in general, we're somewhat limited from the single pencil beam measurement that we get from DLA detected in absorption and perhaps imaging or spectroscopy of the host galaxy. And an additional, would like to know more specifically what gives rise to the neutral gas that was detected in the DLA absorption, what physical processes are responsible for producing this population. That could include things like originating in the ISM or the extended neutral gas disk of a galaxy. It could be the CGM or intergroup gas. Phenomena like outflows or accretion, so like non-equilibrium phenomena. And in general, we aren't able to say that precisely. But one piece of information that can allow us to get at that much more clearly is if we have H1 21 centimeter emission that allows us to spatially resolve and spatially map the neutral gas content of the host galaxy, and from that be able to make morphological or kinematic arguments about the connection between the galaxy, the ISM itself, and the neutral gas that produces the DLA.
Yep. Cool.
So there are quite a limited number of such systems that have been detected to date. There's only 2 systems in the literature where spatially resolved 21 centimeter observations have been obtained for DLA host galaxies or host environments. And here we're able to add a third case that is actually the first known instance in which we detect spatially coincident 21 centimeter emission at the location of a DLA that's detected outside of the stellar body of the galaxy. Nice. So this is quite powerful pairing of the COS observations with the MALS observations that allow us to look at the neutral gas from both the 21 centimeter emission and absorption standpoints. So
very cool.
That's the context and the motivation for this study. So I can briefly talk about the data that we have. So
yes.
As I mentioned, the main observational tool that we have from CUBS is the HST-COS absorption line spectroscopy that is what produced the DLA detection. We also have ground-based shell spectroscopy that gives us a higher spectral resolution handle on associated ions. And from that program as well, we have observations from the MUSE IFU, as well as galaxy redshift survey information from the Magellan telescopes. So we're able to probe both the galaxy population in the field, as well as from the IFU observations, the optical emission line tracers of the stellar components and the associated warm ionized gas. So that comes from the CUBS side. And then on the MALS side, we have the 21 centimeter observations that come from Meerkat. And here we're able to both map the H1 21 centimeter emission, as well as look for 21 centimeter absorption against the radio bright quasar.
Right.
So that's our sort of array of observations that we're working with here.
Wow.
And I think we can go to figure 1.
Sure, let's take a look at figure 1. There's our results. We've got an awesome table here on column densities. And
Yes.
figure 1. There we go. Let's zoom out a little bit and get the global. Okay.
Great. So this is a summary of what we see from the COS observations. So we can see at the top left, this is the damped Lyman alpha profile. We can clearly see the damping wings.
Yep.
And this gives us an H1 column density of about 20.6. So this is clearly in the DLA regime.
Definitely.
And we see quite a few associated low and intermediate ions that are shown in the blue and the pink boxes here.
Yeah.
So this is both, most of these come from the COS observations, but we also have from the ground-based shell that comes from Mike on Magellan, the calcium-2 absorption lines that give us a better handle on the kinematic structure of the absorber, because these are higher spectral resolution observations. So it appears that this is quite a kinematically simple system. We only need a single absorption component to well reproduce the absorption profiles, and that single component captures the range of these low and intermediate ions to within the signal to noise of the data.
Why the separation into blue box and pink box?
Yeah, so it's meant to roughly distinguish between low and intermediate ions. So the pink box are slightly higher ions. So there's some evidence for sort of intermediate temperature gas. We see the carbon-4 lines. Those have a somewhat broader line width, broader Doppler parameter. So potentially they originate from some sort of interface species or on a larger spatial scale than the lower ions. But our silicon-4 is contaminated and we don't detect N5. So
yeah, not there at all.
Yeah.
Yep.
So that's the extent of our constraint on the multi-phase nature of the gas. But certainly some multi-phase nature from the neutral gas to the carbon-4. And a key takeaway from the analysis of these ions in bulk is look at the chemical abundance pattern and the metallicity of the gas.
Right.
So that's the upper right panel, where on the vertical axis, we've listed a number of elements where they're ordered from least refractory at the bottom to the most refractory at the top.
Yes.
So the elements at the top are most likely to be depleted onto dust grains in a dusty medium.
Yep.
So the green points here are the best constraints on the metallicity and the abundance pattern. So here, our best constraint on the metallicity comes from sulfur, since sulfur is not highly depleted, even in the presence of dust. So from our sulfur to hydrogen ratio, we can constrain the DLA metallicity to be about 10% solar.
Yep.
And I'll come back to this red circle here. That's a comparison to the ISM of the host galaxy.
Oh.
But this is sort of a hint at consistency in this figure as well.
Exactly. Yeah.
So the other main takeaway message here is when we go to the more refractory elements, the iron and the calcium, we see lower ratios with respect to hydrogen than expected from the sulfur to hydrogen abundance. So that suggests depletion, dust depletion.
Yeah.
So it appears this is relatively low metallicity, about 10%, and dusty is the main takeaway from the COS observations.
Yep. Very cool. Very cool. Okay.
So this was our first look at this system. And from there, we were able to pair this with both the Meerkat observations as well as the Muse observations to get a picture of the nature of the host galaxies. So that's shown in figure 2.
Ooh, very nice. Very nice. Zoom out. There we go.
Yeah, so starting with the top panel, if we first just look at the multiband image in the background, we see right away that there are 2 blue dwarf galaxies that are at close projected distance to the quasar sightline. So the quasar sightline is shown, by the purple X. And we can see the 2 galaxies, we call them G1 and G2. They're at impact parameters of about 6 and 30 kiloparsecs.
Ooh, wow.
So they're quite close to the quasar sightline. And the redshift of these galaxies is essentially identical to the redshift of the DLA. So these are close both in projected distance as well as in velocity. And we know from the Cubs Galaxy Redshift Survey, just from photometric redshifts, from the Dark Energy Survey in this field as well, we have quite a good handle on the galaxy population in the field. And we know that these 2 dwarfs are quite isolated. So they don't have any massive companions above about 5% L star within a few hundred kilometers per second and a few hundred kpc. So the evolution of these galaxies doesn't appear to be, or is not influenced by the halo of a massive companion or the presence of a massive companion. So it's a nice sort of contained system to study the impact of, in this case, a dwarf-dwarf interaction on the gaseous content and surrounding gaseous medium of these galaxies. So that brings us to the Meerkat 21 centimeter observations. So that's still in the top panel. The yellow and green contours show the results of the 21 centimeter emission mapping. So we see extended neutral gas detected around both around the stellar bodies of both galaxies, as well as what appears to be a tidal stream connecting the 2 galaxies. So the contour that's marked with the thicker green line shows the threshold for a DLA for neutral gas.
Oh, nice.
And you can see that the quasar sightline samples more or less that DLA contour in the 21 centimeter map. So we find quite consistent column densities from both the emission as well as the absorption, and we see that this sightline is sampling what appears to be the outer perturbed regions of G1. These regions are also appear to be connected to this larger sort of gaseous envelope that's surrounding these two systems, and that is strong evidence for these two being an interacting dwarf galaxy pair that has perturbed both of their gas reservoirs in this way.
Yep, very nice.
And we see some additional evidence for that interaction in the stellar component. So in the bottom panel here, this is showing Muse white light images of the two galaxies. So this is selected from a region that excludes emission lines to look just at the stellar continuum. And both galaxies have some evidence for some tail-like or tidal-like features. In the case of G1, that there's a bit of a stream feature that points towards the quasar. I should note that the quasar is at cosmological distances. It's at a redshift above 1, so it's not having any influence on this environment. So it's coincidence that it points towards the quasar, but potentially related to the DLA detection.
Yep.
And in G2, there's this hint of a potential stellar stream pointing towards its companion. So consistent with this picture of interaction. Yeah. So also in that figure, we're showing the H alpha contours that come from the Muse observations. So this is looking at the warm ionized gas associated with, in this case, the ISM of these galaxies. So we don't detect the warm ionized gas really beyond the extent of the stellar component. We don't see H alpha emission at the location of the quasar. There's a feature here that comes from the residuals from the quasar light subtraction. So that's not a true detection. There's a small cloud detected at about 2 kiloparsecs from the quasar itself, but in these observations, we don't detect spatially coincident optical line emission at the DLA location. But we do get from Muse a range of emission lines that are ultimately useful for looking at the gas phase metallicity of the galaxies. So we'll come back to that in a future figure. So that's the general picture of the system, and sort of a key takeaway of the paper, which is that the system is clearly interacting and has this extended neutral gas envelope that has given rise to this DLA and in the outer outskirts of the at least detected portion of the envelope.
Very cool. Beautiful image.
Yeah, thank you. It was a very fun data set to be able to put together. So the rest of the paper is essentially strengthening the case and looking more specifically at the physical properties of the ISM as compared to the DLA to sort of confirm the origin of the DLA gas as former ISM material.
Yes.
So in figure 3, we look at that from a kinematic standpoint. We go through some. Yeah, some properties of the galaxies. I can mention maybe
Sure.
mention the stellar mass of the galaxies. These
Yeah.
are a stellar mass of about 8.5. They're
Okay.
about have
It's funny.
Identical masses within the uncertainty.
Yeah.
So these are quite
Twins.
yeah, they seem to be twins in a lot of ways. And
Wow.
their H alpha star formation rates are about 0.03, 0.04. And the total H1 mass, which appears to be approximately distributed between the two galaxies, is it's around 10 to the 9 for the full system.
Right. Wow. Our twins.
Yeah, which is interesting.
Yeah, very cool. Anyway, I just thought that was a lovely table. So okay. Figure 3. Here we go. Let's do zoom out. Oops, a little too much there. Let's try there. Okay, what do we got here?
Yeah, so this is looking at the kinematics for both the neutral gas and the ionized gas. So on the left panel, we're looking at the line of sight velocity, and on the right panel at the velocity dispersion. And the top, we're looking at the meerkat observations. So this is, again, that full field where the individual galaxies are outlined in white.
Yes.
And the size of the meerkat beam here is large compared to the individual pixels. So we can't make particularly strong statements about trends in the in velocity pattern across the system, but we are able to say that, so here the velocity 0 point is set by the DLA, and we can see that in general across this full envelope, there's not significant velocity shear. Like the full envelope is at quite consistent velocities within 10 or 20 kilometers per second of the DLA itself. So if there's significant shear, then it's in the plane of the sky.
Yes.
And we do see quite consistent line of sight velocities between the H1 and the H2. So in the bottom panels, the Mu's H alpha velocities are quite well matched to the H1 velocities, and have a similar picture of being generally kinematically quiescent. So even though these are appear to be interacting galaxies with some disturbance on large scales, the ISM of the galaxies themselves doesn't look particularly anomalous. So and similarly in the line widths. So in general, the H1 line width is about 10 or 15 kilometers per second, which is consistent with the DLA itself. There's some evidence that the H2 line width is a bit broader by maybe a factor of 2, but in this case, the optical emission lines are not resolved in the Muse observation, so we can't read too far into the interpretation of that line width. Potentially a bit of turbulence from star-forming regions, but overall, the takeaway message kinematically is that this is, for being a disturbed system, it's relatively kinematically quiescent, and there's quite a bit of consistency between the DLA velocity and line width and this gaseous envelope.
Fireworks are coming for this system. Very cool. Very cool.
So the last main piece that we look at is the optical emission lines, with the primary goal to look at the metallicity and the dust content of the ISM for these galaxies. The best tracer that we have of the gas phase metallicity for either of these galaxies comes just from the brightest star forming region in G1. So that's shown by this yellow aperture shown in the upper left panel.
There we go. Bang, there's yellow.
Yeah. So just within that region, we detect both an auroral and a nebular line from sulfur-3, and that gives us a direct measurement of the electron temperature and a direct measurement of the sulfur abundance that we can then compare to the sulfur abundance that we see in the DLA. So from this,
yep, I'm with you.
The abundance that we see in G1 from that direct measurement is about 10 to 20% solar, which is quite consistent with the about 10% that we saw in the DLA prior to a dust correction. With a dust correction, that becomes something like 15%. So they're quite consistent. And that was that red circle in the figure 1 where we show consistency of ISM metallicity as well as that's right. Yeah. So the alpha element abundance is consistent between the ISM of G1 and of the DLA. Nice. So that strengthens the picture that this gaseous envelope is former ISM material that's been perturbed by the interaction and distributed to larger scales. And there's additional strong line metallicity diagnostics that we can use based on the N2 to H alpha ratio and other line ratios that look both at the metallicity as well as the excitation state of the gas. And in general, from the line ratios, the takeaway message is that the metallicity is seems quite consistent across the bodies of both of these galaxies. G2 might be slightly more metal enriched than G1, but there's nothing sort of particularly striking about any metallicity variation. So these are, this is sort of sticking with the theme of consistency in the DLA properties and the dwarf properties. And one more piece to add to that is the dust content. So from the Balmer decrement, we can measure the reddening in both galaxies, and the values that we find here, the EB minus V is something like 0.05, 0.1 for these galaxies, which is typical for galaxies of this mass. So they appear to be dusty in a typical fashion. And again, having seen the dust depletion in the DLA, both the ISM and the DLA have this approximately 10% solar, sort of dusty nature to them. So that puts together this coherent picture of this envelope being perturbed ISM material that has likely been drawn out from star forming regions. So showing some evidence of metals and dust being distributed on spatial scales that are larger than the stellar component of the galaxy itself. Yes. And in this case, the driving physical mechanism for that appears to be the interaction itself and perturbing the envelope. So cool. That's the key, or a key, I think, takeaway message for this paper, in addition to the ability of interacting dwarf galaxies to increase the cross-section for producing DLAs. We see both that as well as are able to look specifically at the gas properties and argue for this increased cross-section is coming from redistributed ISM material. Right. So awesome. We look in the discussion a bit at scaling relations between the the optical size, the H1 size, and the H1 mass, where this system is, despite being perturbed, is generally consistent, like within the errors with known scaling relations.
Right.
So these scaling relations appear to be preserved even kind of in even through the processes that produce these perturbations.
Because it's not that huge yet. Yeah, very cool.
And we also do a bit of a back of the envelope calculation to look at whether we see evidence of or whether we expect tidal stripping to have occurred by looking at the tidal stripping radius given particular separation and respective masses of the two galaxies, and show that we expect the truncation radius to be about 10 to 13 kiloparsecs, which is larger than the observed size of the stellar bodies. So
Good.
It seems that either these galaxies are just intrinsically small enough that they have avoided like significant stellar truncation, or in the past they this is assuming that their current separation was their closest distance of closest approach. So if they were in the past had a closer approach, that could have been responsible for truncating them to their current smaller size.
Yeah.
So
Nice.
overall, the key takeaway here is adding sort of to the literature this first instance of a spatially coincident detection of the 21 centimeter emission with the UV selected DLA outside of the stellar body of a galaxy, and the interpretation that this is due to the redistribution of the ISM through dwarf-dwarf interactions. So this motivates the need for dwarf galaxy interaction models to produce this effect, to produce this puffing up of the gas disk. And we see examples of this potentially locally in the Magellanic Stream, where it's a different system in that it's falling into a massive halo, and there may be environmental effects, but the evidence for production of the stream from tidal interaction between the two galaxies suggests some similarity and potential comparison of an isolated system and a system in a massive halo could point to what aspects of the non-isolated system may be due to environmental effects. So I think building up a larger sample of these interacting dwarf galaxy pairs that have these sort of careful observational studies at low redshift could help disentangle this the effects of environment from the effects of the dwarf-dwarf interactions themselves.
Very nice. Very cool. Very cool. Very comprehensive work. Very cool.
Thank you.
Erin, thank you so much for walking us through your very lovely APJ letter.
Thanks again for having me. Yeah.
Sure. So let me ask, since you mentioned it a couple of times, or at least once there toward the end, where do you think we go with this over the next couple of years? How do we hunt for more of these dwarf interacting pairs? Is there other wavelengths or other observations that could be done on this particular interacting pair, and so on? So just kind of, where do we go?
Yeah, so I think it's a particularly interesting time for this work in that as the SKA precursor facilities and the SKA itself come online, we're just continuing to build up these really deep and spatially resolved maps of the H1 content of nearby galaxies, and that in and of itself is going to just give us so much of a richer picture of both the ISM and the CGM of nearby galaxies. And I think what's particularly critical right now is that we also have the Hubble as a resource as well to continue the UV perspective on this. So the ability to pair the UV perspective with the 21 centimeter perspective, while both of those communities have access to our current observing resources, will be particularly interesting. So I think the 21 centimeter observations they give us the best sense of where to look, and that they give us these quite exquisite maps, and from there taking opportunities to follow up in the UV where we're limited by the background sources, but doing the best that we can to select systems that are probed in these multi-wavelength perspectives will hopefully add statistics to these kind of studies.
That'll be great.
And yeah,
very nice. Well, I look forward to this developing over the next couple of years as these facilities come online and follow-up work is done and people do some models of these things. That would be great. So very cool.
Yeah.
Thank you so much.
Thank you too.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.